Alright, today we're going to continue with graphing and how it relates to different derivatives. First off, just sort of as a refresher here, in these two graphs here, we have, in this case, two graphs, in this case, three graphs. So we want to think about which one is the original function, which one is the derivative, and in this case, the second derivative. Well, we know if we have a quadratic, its derivative is going to be a line. The slope here is 0, which is why its derivative is 0. So this one is f, this one is f prime. Here, we've got a cubic, a quadratic, and a line. So the cubic is going to be f, the quadratic will be f prime, and the line will be the second derivative. But looking at the features, so if this is our original graph, it's increasing, then it's decreasing, then it's increasing, which is why its first derivative is positive, then negative, then positive. It's concave down, then concave up, so its second derivative is negative, then positive. And those are the things that we're going to be looking at today. Okay, so if y prime is 6 times x plus 1 and x minus 2 squared, we're going to find out where there's a local max, a local min, and points of inflection. So max and min we're going to get from the derivative, which we are already given. Okay, so I'll do my number line chart because that's a good way to organize our information. Okay, there are two critical points here, one at -1 and one at 2. Those are the things that make our derivative 0. Okay, so using our number line charts, this one is going to go from negative to positive. This one, since it's squared, is going to be positive for every value except for 2, where it'll be 0. So on my number line chart, we've got a negative times a positive times a positive, and a positive times a positive. So that means our graph is decreasing, then increasing, then increasing. So we have a minimum here, and then this will be a plateau. So where is there a local maximum? There is not a local maximum because there's no switch from positive to negative. We do have a local minimum at x equals -1. For point of inflection, that's going to come from the second derivative. So I'm going to go ahead and do the second derivative, which is going to require a product. So we're going to have 6 times the derivative of x plus 1 x minus 2 squared plus, I'll just go ahead and put the 6 there as well. The derivative of x minus 2 squared times x plus 1. So derivative of x plus 1 is just 1. So we're going to have 6 times x minus 2 squared plus 6 times the derivative of this will be 2 x minus 2. Derivative using the chain rule, that's just going to be 1. So we're good. Okay. So we have this. We want to come up with a sign chart. So we prefer multiplication over addition because I can figure out the signs easily. So I'm going to factor out a 6 and an x minus 2. Okay, so if I factor a 6 and an x minus 2 out of this, I'm left with x minus 2. Here, I'm going to be left with, I pulled out this and this, x plus 1. And then we're just going to simplify in the parentheses here. So the 2's cancel, so I'm left with 3x which is going to be 18x times x minus 2. So for the point of inflection, I'm going to do a number line chart for this. So 18x, x minus 2, and can align for the second derivative. There's two critical points here at 0 and at 2. Okay. So this one goes from negative to positive. This one goes from negative to positive. So this is going to be positive, negative, positive. So for our graph, this is concave up, concave down, concave up. So there's an inflection point here, an inflection point here, because when concavity switches, we have an inflection point. So at x equals 0 and x equals 2. Okay, so here we are given the graph of f prime. So that's an important thing to note. The domain is from -3 to 6, and we're going to answer the certain questions. So we are given the derivative. This is not the graph of the original function. Okay, so first, critical points. Critical points are going to be when the derivative is 0, which in this case is going to be here and here. So when x equals -2 and x equals 4, our reason is because f prime of x equals 0. So our justification is always that. Okay, and here's a trick for dealing with some of these other ones. Because looking at this graph can be a little bit deceiving. Because when you see increasing, you want to say, well, it's increasing here and it's decreasing here. But this is the graph of the derivative. So what I'm going to do is I'm going to take this information and turn it into a number line chart. Okay, this one has a set domain. So I'm going to put the endpoints, -3 and +6 on there, and I'm going to label it as EP. Okay, the critical points, we already established were -2 and 4. So our derivative is 0 here, 0 here. Between -3 and 2, our derivative is negative, okay, because these values are below the x-axis. From -2 to 4, all of this are positive values. Here, we have negative values again. So our original graph, which we don't have in front of us, is decreasing, then increasing, then decreasing. So this is going to be a minimum, this is going to be a maximum, and I'm going to ignore the graph. I'm going to look at my number line chart and get my answers for all of these from this. Okay, so where is the graph increasing? That's going to be from -2 to 4, and all I'm going to say is the reason, f prime of x is greater than 0. That is all you have to say, that is all you should say. Decreasing from -3 to -2, so make sure you include those endpoints, because it's not just when x is less than -2, it's specifically here, and then from 4 to 6, reason, because f prime of x is less than 0. Where does it have a relative minimum? Right here at x equals -2. From the first derivative test, we can say, because f prime of x switches sign from negative to positive. Okay, where does it have a maximum? Right here, we've already established that. So x equals 4, because f prime of x switches signs from positive to negative. Okay, and then where is the graph concave up and concave down? So that's going to be for the second derivative. I don't have an equation here, I just have the graph to work with. Okay. The second derivative is going to be the derivative of this graph. So what we are interested in is the slope. So this was a positive slope, then a negative slope, then a 0 slope, then a negative slope. So the critical points on this graph are going to be at -1, at 1, and at 3. Okay. So my derivative of the derivative is actually undefined at all of those locations because they're corners. Okay, but we're going to look at the slopes. So the slope is positive, which means the derivative of this graph is positive. The slope is negative. Slope is 0, so the second derivative there would be 0, and then negative again. So this graph is concave up, concave down, and there's no concavity there. It's just going to be a line. So our graph is concave up from -3 to -1 because f double prime of x is greater than 0. Even though we arrived at this conclusion looking at the slopes, this is your justification. Okay, it's concave down from -1 to 1, and from 3 to 6. Our reason, because the second derivative is less than 0. Okay, so this one's going to be similar. The figure shows the graph of f prime. The derivative of f and the domain of the real numbers is from -10 to 10. Okay, so for what values of x does the graph have horizontal tangents? That means where is the derivative equal to 0? Well, this is the derivative. Okay, so where this is 0 are going to be the x-intercepts here. So the critical points are at x equals -7, x equals -1, x equals 4, and x equals 8. Okay, so before I answer these following questions, I'm going to do the same thing I did in the last question, where I'm going to turn this into a number line chart. So I'm looking at numbers and pluses and negatives instead of an actual graph. So this is the number line chart for f prime. Our endpoints are at -10 and +10. Our critical points we've already established are at -7, -1, 4, and 8. Our derivative is 0 there because that graph is there. Then we're looking where is the derivative positive and negative. So it is negative here, positive here, negative here, and positive and negative. So the graph of f, which we do not have in front of us, is negative, positive, decreasing, increasing, decreasing, increasing, decreasing. So we have a minimum here, a maximum here, a minimum here, a maximum here. Okay, so now with that, I can answer the follow-up questions. For what values in the interval do we have a relative maximum? So that's going to be at x equals -1 and when x equals 8. Okay, our justification, no matter how we arrive at the answer, is always from the first derivative test, f prime of x switches signs from positive to negative. Okay. For what values is it concave down? So I'm going to do another number line chart for the second derivative. Put my endpoints. Okay. Looking at the second derivative is going to be the first derivative of this graph I'm looking at. So the slopes are 0 here, 0 here, 0 here. So my second derivative is going to be negative, or 0 at -3, at 2, and at 6. Then we're looking at the slopes. So the slopes from -10 to 4, slopes are positive. From -3 to 2, slopes are negative. From -2 to 6, our slopes are positive. And then from here to here, slopes are negative. So the original graph that we don't have in front of us is concave up, concave down, concave up, concave down. There's inflection points at all those changes in concavity. So for what values of the x is concave down, that's going to be from -3 to 2, and then 6 to 10. And our justification, no matter how you arrive at the conclusion, is simply because the second derivative is less than 0. Okay, and then the inflection points we established were at these 3 changes in concavity. X equals -3, x equals 2, x equals 6. Why? Because f double prime of x switches signs. Okay, so in this one, what is the relationship between f of 2, f prime of 2, and a second derivative at 2? So we're interested in this location. F of 2 is a positive value. I mean, we can establish it's 3. F prime of 2 is the derivative here, is the slope here is going to be 0. And the second derivative, since our graph is concave down, is going to be negative. So my relationship is the second derivative at 2 is less than f prime of 2, which is less than f of 2. That's negative, that's 0, that's positive. Okay, our next example, for all x in the closed interval 1, 4, the function is concave up. Which of the following tables could be the values of g? Okay, so what we're looking for, the second derivative tells us concavity. It also tells us the change in the slope of the derivative. Okay, if the slopes are increasing, then we have concave up. So what I want to look for is, these are all 1, 2, 3, 4. So looking at here, we're going up 3. Here I'm going up 1. Here I'm going up 4. So that, if I look at the change, is inconsistent. Here it's 2. Here we're going up 3. Here we're going up 5. Okay. This is 5 to 5. Again, it's not a steady increase. Here is -2, -2, -2. So if I took the derivative of that, it'd actually be 0. So the ones I'm looking for here is the change is increasing here. So this is the graph that would be concave up. So that is more about graphing.